All right, so we're going to walk through tuning this mount. It's an L500 with the 17 installed. And we know for sure that the tuning right now is bad. It was tuned for no OTA. So that's, we're going to see some bad things happen when we first turn on the altitude motor especially. So first thing we do is we start PW tools. Eventually this is going to be its own separate application, but one part of PW tools is this ElmoTester program, which we'll bring over here. And there are two buttons up here, one to connect to the azimuth axis or one to connect to the altitude axis. Right now you can only be connected to one at a time. So let's do altitude first. Connect, and it's going to warn us here that the axis hasn't been homed yet, so we can just make a note of that. Now if we turn the motor on, I don't know if you can see it quite in the video, but it's shaking up and down quite a bit.
Right.
You can see it here in person. So let's, and you can actually see here the position is oscillating quite a lot too. So let's turn that off. So we're back in free motion mode. And to do a tuning, first thing you can do is, well, let me point out one other feature first, is if you go to Tools, Graphical Tuning, and we're going to come back to this screen in a minute, but I do have some what I call universal parameters. So we can say load universal altitude parameters, and it populates this window with parameters that are kind of always safe to use. And then we can send those to the controller by going parameters, send to controller. And now when we turn the motor on, it doesn't shake anymore. It's very soft.
Okay.
But, so you can displace it very easily if you push on it. But at least you could, home the telescope if you wanted to. You can do tools, homing, and find home, and it'll go through and initialize the scope. So this is important, especially if you're working on a scope remotely. You want to have some notion that you can believe the position numbers so that you know you're not pointing it at the ground and you're away from a hard stop. Okay, so that's kind of an aside. You don't really need to do that soft tuning every time to begin with, but it's a way of just getting to a mode where it's at least safe to move the telescope electronically. So now, let's close that, close that. The way you begin tuning is you go to Tools, Frequency Sweep. That brings up this window. This will eventually be integrated with the other tuning tools, but right now it's a separate tool. And what we're going to do is, I actually like to start at 2 Hertz and end at 1250 Hertz. So over 100 points in this interval, it's going to oscillate the telescope twice per second, and then 3 times per second, 4 times per second, all the way up to 1250 at some appropriate spacing. And it's going to be driving 1.5 amps through the axis in this sinusoidal fashion. That's what's going to create the motion. And we're basically measuring at each frequency, if we excite the motor with current at this frequency, how much movement do we get as a response? So we're characterizing the mechanics of the whole system right now. So we'll just hit start. By the way, this retry low quality is an experimental thing. I'm going to turn that down right now. So you might be able to tell that it's oscillating back and forth. The reason it's gradually moving down right now is because the scope is slightly front heavy. And so it's kind of moving its way towards a neutral balance position.
Right.
So it's getting close. I do have a planned fix for that where it will actually maintain its position on average. It'll just in the background have a very low background current injected that'll just hold its position while it's doing the sweep. But you can see as it's oscillating back and forth at different frequencies, so it's now up to 3.3 Hertz. And this top graph is measuring how quickly the axis is moving back and forth at that frequency. And then the bottom graph is how much the axis is lagging behind at that frequency. So if your current is going up, down, and the motion is going down, up, that would be 180 degrees of phase lag. Or if it's delayed by...
This is the phase,
yeah,
sort of?
Yep. So typically, at low frequencies, this starts out around minus 90 degrees. 90 degrees of phase lag is just what happens when you take current, which produces torque, you integrate that, or produces torque, which produces acceleration. You integrate acceleration to give velocity, and when you integrate a sine wave, you get, another sinusoid that's offset by 90 degrees. So it's now going higher and higher frequencies. And it starts off at these low frequencies. It takes a while to make any progress. But as we get to higher and higher frequencies, it's going to speed up a lot. This whole process with the settings I have is going to take about 2.5 minutes. So we're coming up across the 10 hertz level right now. And by the way, we are on a pallet, if you look down. So, and the pallet itself is not perfectly flat, so it can rock back and forth. And so some of these features you see here aren't the mount or the telescope, it's actually the pallet shaking back and forth.
Right.
But the nice thing about this is we can actually tune around the fact that we're on a pallet and have it still perform well even under those conditions. So we're crossing 20 hertz now. And now you can't really see it moving anymore. If you just lightly put your finger on there, you could feel it vibrating. And then as we get to higher and higher frequencies, it'll eventually get to the audible range where you actually hear it making tones. We'll hear that in a second. So 60 hertz, 70 hertz. You see the spacing is increasing, and it's going faster now. And we're just starting to get into the audible range. You can hear it a little bit. This is actually taking longer than it normally would because I added a delay at each new frequency, a 1 second delay, to kind of give it time to settle into its new frequency before measuring. I think in the final version this will go through a lot faster. 5 more samples to measure. Okay, now we're all done. And after recording something, I like to, you can go up to File, Save As, and we'll save this data that we just recorded. We'll just put it in a temporary folder here. I'll call it altitude with CDK17 on palette. And that way, if we ever want to come back and readjust the parameters in the same configuration, we can just load this same data, adjust the parameters, and reanalyze it. Okay, now to go from here to the analysis stage, you can just click the Analyze button. It brings up this new window. And we have some interesting plots here.
So this shows the way the tuning you have in there right now, which is sort of soft but safe, how that tuning would react to now this
Exactly.
setup.
Yep.
Right.
Yeah, so we're taking our characterization of the mechanics. We're doing some mathematical transformations on that based on our tuning parameters. And let me just point out that if you want to actually retrieve what's on the mount right now, you go to Parameters, Read from Controller. It happens that we had already, since we'd already been in the screen once, we already have those numbers. So the very first time you do this, you just get some kind of meaningless defaults here.
Right.
So when you first open the screen, you should always do Read from Controller.
Okay.
until I make it automatic.
Right.
Okay. And the most interesting graph that we want to look at right now is this one in the top right corner. So it's kind of a funny looking graph, but once you get used to it, it makes a lot of sense. Let's look at the left-hand graphs first. So this is basically the same stuff we were seeing before, where the top is the amount of movement you see at each frequency, and the bottom is the amount of phase lag you see at each frequency. Now, if we take this top right plot, it's basically like take this point right here as your y-coordinate, and this point right here is your x-coordinate. That corresponds to probably this point right here on this plot. Right. So frequency, rather than being along the axis, frequency is increasing along this line, or along this curve. And actually, as you move your mouse over, you can see this first point right here is our 2 hertz point. And this is our, that's our 112 hertz points, which is one of these guys up here. Yeah. So frequency is increasing along this curve. And it gets kind of scribbly at the bottom when you get all these changes. But the thing we're aiming for is for the low frequency part of this curve to be up along this 0 dB contour as much as possible. Or we want as much of this curve above the 0 dB contours as possible, because that's what gives us stiffness and responsiveness. And simultaneously, we don't want anything to get into the red circle, because that's what causes instability. Okay. So we adjust our parameters over here. You can select a row, and then I'm going to turn off all filters just to begin with, and we're going to see some examples of bad tuning. So this is just using the P term and the I term in the velocity controller, and then a P term in the position controller, which we'll get to in a minute. So basically, as we slide this value up and down, the whole curve just moves up and down. So that's a very intuitive one to work with. Yeah. And what we see here is, that's sort of the best we can do without any filters installed. And if we're happy with that, or we're done analyzing it, we want to put it on the controller. Let's say send to controller. So now the mount is actually using these parameters that we've just finished analyzing. And we come back over to this window to turn the motor on. You see that it's still really soft. That's a terrible tuning. Now, what would happen if we tried to make the mount stiffer by increasing this value? Remember, we're trying to bring this part of the curve up as close to 0 dB as possible. So we could do that just like that. Then what happens? We send the parameters, and then as soon as we excite the mount, we get a bad sound. And that bad sound is probably at that sound is probably at around 600 to 700 hertz, which is the frequency of these points. And that's passing through this instability region, so that's no good. So the goal...
Once you've sent parameters to the mount, do you have to save them? Like, you turn the mount on and off, does it remember them?
Yeah, the last thing that we'll do is save these parameters to flash, which will record them in the mount so that you can power cycle and reload the same parameters. Okay, so it should be pretty obvious that we need to push this high-frequency stuff down to make room to lift the low-frequency stuff up. Okay. And the way to do that is with filters. So we'll add a first velocity filter. You almost always want to add a low-pass filter. Low-pass. And once you select the low-pass filter, you get a few filter parameters you can change. So the frequency here is basically the frequency above which you start to push down your gain. And it starts at very high frequency, which has almost no effect. But as we bring this down, we see that eventually we start to push those that high frequency stuff.
Oh, I see. So you're on the filter, and now this slide changes that filter value.
We can change the selected value with the slider. Or you can, if you want to try a value, you can just click there and type it in.
Right.
And hit enter.
Okay.
But the slider is a nice interactive way to get a sense for what this parameter is changing.
Nice.
So if we look at this graph, the top left graph, it's pretty obvious that as we lower the cutoff frequency for the low-pass filter, everything above that is getting pushed down.
Yeah.
So that's what we're seeing here. But at the same time, we're also causing more phase lag in lower frequencies. So it tends to push the low-frequency stuff to the left in this graph.
Right.
And we're kind of doing a trade-off between pushing down the high frequency but not bringing in the low frequency too much. So let's say that we want to try for right there. And now we have more room to push the rest of this curve up. So let's try that and see how it looks. Send to controller, turn it on, and no more buzzing sound, and quite a bit stiffer than it was before. And the way you check stiffness is you don't really crank on it and try to fully push it out of position. You just sort of, push on it until you just begin to feel it move. And if it feels kind of spongy, then you want to try to boost up the tuning a little bit more. If it feels really stiff, where it's like fighting back against you the instant you start pushing, then that's a good tuning. It's going to be able to reject wind and other disturbances better. So another trick we can do is add a notch filter, which is probably the second most useful filter in this set. So filter 1 is going to remain in its low pass configuration. And by the way, this other term, damping, you can slide back and forth and kind of see what effect it has too. So kind of a more localized effect around the cutoff frequency. But for a notch filter, this is kind of a more targeted approach. Like if we see a single point that's kind of raising up high here, like this one above 100 hertz, that might be a good one to try to, push down a narrow range of frequencies. So let's slide this down to about... And right now it's not doing anything because the magnitude of our filter is 0. It's not everything in this filter is getting multiplied by 0 in the end, so it's not doing anything. It's not until we start to increase that number that we can see the effect that we're having. So let's just set it to maybe 10 to start, and then sweep through our frequencies. And we can see, like right there, we're starting to get rid of some of that noisy stuff. But we're also bringing the low frequency part of our curve into the circle. So it's a little bit of a trade-off here. And what I like to do is kind of pick isolated frequencies with the notch filter and then see if we can increase our low-pass filter to gain back some of this phase margin that we're losing. And over time, you just learn how to play around with these values until you sort of get what you want. And I won't spend too much time on it for the sake of this video, but let's say that that's pretty good. We can increase our velocity gain a little more. And then the velocity integral number, this is another pretty easy one to understand. It just brings the low frequency part left or right. So maybe that's kind of good there. Just the top part of the curve is coming in.
Yeah.
So let's send those to the controller. And that's feeling a little more stiff. And then the last thing that you want to tune once you've got your velocity parameters looking good, then you want to tune your position gain right here. And for that, we look at the bottom right chart. And this is another pretty easy one to understand. You just select position gain and slide this up until the curve is basically touching. Send that to the controller. Yeah, and that's feeling really good now. Go ahead. Okay, so that should be a good tuning. And then you want to kind of test it. Just if you look at your following error, which is tracking error, essentially. So this is showing you the instantaneous tracking error, and the RMS number is up here. So we're kind of standing still. We're below 0.1 arc seconds RMS. And we can try moving around here. Let's move up 5 degrees a second. And even moving 5 degrees a second, we're still kind of around 0.3, 0.4 arc seconds RMS with this tuning. So that's really good. And then, if you kind of pull this out of position and let it go, you can see that it comes back to 0 very quickly.
Yep.
Okay.
So you're going to save that?
Yeah. So actually, it looks like it is oscillating a little bit right now. So let me decrease one of our gains slightly. Maybe like that. Just give ourselves a little more room. Send a controller and see if that calms it down. Yep. Yeah. So I think the problem with the way I'm sampling right now is sometimes you get these big jumps between high frequencies and you miss small features that are actual. If you sampled more finely, this would actually enter the circle.
Yeah.
So I have an adaptive sampling approach that I'm developing right now to improve that. But let's say we're happy with these parameters. Then you just go to Parameters, Save to Flash, and it'll tell you what you're about to do. Hit OK. A second later, it should be done. So now if we power cycled this, and turned on the axis, it would be using these same parameters.
Good.
Yep. And then to tune azimuth, it's the same basic idea. We'll remove all the previous sweeps that were loaded in here. We'll disconnect altitude, connect azimuth. It's warning us we haven't homed. But azimuth tends to be less sensitive because you have so much mass in that azimuth is moving already that with an OTA versus without, it's not that big of a change in the system. Versus an altitude with an OTA, it's a huge mass. Without an OTA, it's almost no mass. Yes. Okay, so we don't need to go through it right now.
Right.
It'd be the same step. So start a frequency sweep, save it, analyze it, adjust the parameters, and then good to go.
Sounds good.